short people.
I know, we need a phone book or something here. So hi, I'm Katherine Dombrowski. I'm a process chemical engineer with Trimeric Corporation, and I'm going to be talking about getting the CO2 from our Ratcliffe power plant over to the storage field and the pipeline and the design of the surface facilities associated with it. Quickly, let me get oriented here with this. There we go. I had flew through the disclaimer slide. I'll quickly talk about Trimeric Corporation and our co-author on this, PCS. So Trimeric is a process engineering services company just outside of Austin, Texas. There's about 25 of us specialized in process chemical engineering. But we work across a wide array of industries and have specifically experience in CO2 capturing and processing, from pipeline flow analysis to capture from power plants and food and beverage grade CO2 and so forth. A lot of the work you're going to see here today was produced by Project Consulting Services, or PCS. They are founded about 30 years ago in Louisiana. They provide project expertise to the pipeline industry, and specifically have over 20 years of experience in CO2 pipeline. All right, so we've had lots of slides talking about Plant Ratcliffe and how it's very close to the Kemper Storage Complex. So a little bit about Ratcliffe. It's a natural gas combined cycle plant, 2 combustion turbines and 1 steam turbine, 770 megawatt nameplate. So that produces about 287 tons per hour of CO2 when that plant is operating at full load. But that plant can also operate at much lower loads, and at minimum loads, that goes down to 133 tons per hour. We expect over the lifetime of the project we're looking at an 85% annual capacity factor, which means about 2 million tons per year of CO2 coming from Plant Ratcliffe would go to this Kemper storage facility. And if we had a 30-year storage life, that would be 64 million tons. We've also mentioned that there are other Southern Company power plants that are fairly close to the Kemper storage complex. Those could also be potential sources of CO2 for the storage complex, including Plant Daniel, also a NGCC unit that's to the south, and Plant Miller, a coal-fired unit that's off to the east, and that could contribute as much as 17 million tons per year. In addition, we've talked about the industrial sources that are nearby. And so, as we are looking at an initial concept for a pipeline that takes us from Plant Ratcliffe to these injection wells, we want to take into account that there might be future expansion on the site so that we can accommodate that. And so that was in our mind as we were looking at this. But we really wanted the focus of our initial study to be on the pipeline from Ratcliffe to the 2 wells. So we're looking at something that can accommodate about 7,000 tons per day of CO2 coming from Ratcliffe. And we've got 2 wells to take in that CO2. Each of those can be designed for up to 4,000 tons per day, so we need 2 of them. We believe from the work that ARI has done that the required injection pressure is going to be at least 84 bar A. Could be a little bit higher once in practice, but that's the belief right now, and so we wanted to design for at least that. So what we've done over the last several months with PCS is what's called a FEED study, or a front-end engineering and design study. And it's a way to get more detailed into the analysis rather than having some straight lines showing you a pipeline going from the source to the sink. We actually look at the route and what would be appropriate from an environmental standpoint, from avoiding historical areas, from a cost standpoint, what that route is, what kind of engineering would be needed to and implement that route and do the construction. This is an early phase desktop study, so no field surveys have been done yet. The only on-the-ground work that's been done is in publicly accessible areas. So these results are very preliminary from that standpoint. We don't have the on-the-ground studies that we normally do. We also have some environmental information that was gathered by another project partner, ECT, on the land use, the geologic conditions, the vegetation that's nearby, the socioeconomic conditions, the historic and cultural resources to make sure that we could avoid any sensitive areas in the routing. And so what I'm going to show you in the next slides are some of the key pipeline feed study deliverables. And so I've listed many of the deliverables in a feed study. The ones that are in blue are the ones that I'm specifically going to talk about in today. First off would be a basis of design. Any good engineering project, or probably any project, always has to start with a solid sense of what it is that's going to be the basis for what you study. And so the project team spent some time talking about this and considering it in light of the fact that we had these potential future sources that we wanted to tie in, and establishing how big do we want to make this pipeline and how big do we want to make our gathering hubs to be able to accommodate what might happen in the future, realizing that's a big if, and you don't want to saddle the project with too many capital expenses with too many big ifs of what might happen in the future. We also looked at permitting because that's a key component of the schedule of how this project executes. We have a desktop route study, and I'll show you some examples of the maps that were generated to show the pipeline's routing and the detail behind the construction methods. And then we have several diagrams, the process flow diagrams, those are the PFDs, and the process and instrumentation diagrams that show the equipment and how that CO2 is handled along its way. PCS developed a risk register to identify key risks. I'll go over a few of those. It developed a project schedule of how long it would take to implement this project, and then developed a bill of materials for what was needed and developed in total installed costs. One thing that I should caveat here, it's here in bright yellow and red, is that these FEED study results are under review at this point. So these are hot off the press. They have not made it through the full review cycle, but we're showing here as an illustration of the types of results that can come out. So these are all subject to change in some way or another. So first off, I'll talk about the hydraulic modeling parameters associated with the pipeline. And so this has to do with how we're going to size the pipe to accommodate the flow and the pressure requirements of the routing. So from CO2 from Plant Ratcliffe, our maximum flow rate could be 362 tons per hour. And we expect that based on the compression that's been designed for the capture plant, we would receive that CO2 at 1700 PSIG and 120 degrees Fahrenheit. For the wells, you might have heard me say earlier, I think it was 84 bar A or 1200 PSIG was the minimum required injection pressure. And we decided as a team in consulting with ARI that to be conservative in how we did this modeling, we would design to deliver CO2 at least at 1500 PSIG to give us a little bit of buffer in case in future operations things are a little bit different than what was expected from the initial characterization. And each well is being designed for 181 tons per hour. Now, for the composition model, what we ended up doing was modeling a worst case for the hydraulic model, which is actually a fairly dilute CO2 concentration of just shy of 96%. We expect that we know that the CO2 that would come from Plant Ratcliffe is going to be much more concentrated, greater than 99%. But we also know that we may have future tie-ins to other sources that might meet a typical commercial CO2 pipeline spec, which could be as low as this 96%. And so that's what we used in terms of the hydraulic modeling for the sizing of the pipeline. The plot here is showing, or this figure is showing you a process flow diagram for the overall system, and just wanted to show you what the different components are. So starting up here is Plant Ratcliffe, and we have our section has a Plant Ratcliffe station that we have on site to measure flow rate. Then we go through about 5.5 miles of 16-inch pipeline. That takes us to our gathering and distribution hub. Then we have a very short pipeline, just 100 feet, that takes us to one of the injection wells. And then we have another 12-inch pipeline that goes 3 miles to the other injection well. And just to show you some of what's shown on here, so for instance, these are the orifice meters that measure the CO2 flow rate. So we have one at Plant Ratcliffe, and another at the, a few miles down at the gathering distribution hub, so that we can do a mass balance to make sure that we have full accountability of the CO2 that's there from the source to the sink. We also have a pipeline launcher and receiver. So this would be used across this 5.5 mile pipeline in order to do inline cleaning of the CO2 pipeline. So the CO2 itself pushes what's called a pig across this pipeline to do any online cleaning. This is our gathering flow header. So the CO2 from Ratcliffe comes in to here. It's grayed out here, but we have areas for future connections, and we size this at 20 inches to deal with future sources of CO2 coming in. So this is an area where we upsized some of our equipment to accommodate future sources of CO2. So this is future coming in and future going out to the wells is down here. Then from that gathering flow header and distribution, we go this 100 feet over to this wellhead, which takes up to 181 tons per hour of CO2, so it can take up to half of our CO2 from Plant Ratcliffe. It's got its own orifice meter to measure mass flow rate, so for accountability of the CO2 that goes specifically to that well. And this is just showing you that we have tie-ins shown for future well connects for additional sources that could come in, which means that we also sized this short pipe here to accommodate being able to take CO2 to here. So it's not just for size for this CO2, but it's also for here. And then we also have just tie-in connections that we allocated here if we needed an injection pump in order to compress that CO2 for those other wells. For the Plant Ratcliffe CO2, the compression is actually part of the CCS unit that's nearby. And then this is just showing you that we've got this other long flow line going to the other well. And that because we've got this other flow line here that's going several miles, we've got another set of pig launchers and receivers for cleaning that. So that was a process flow diagram. This is just a cutout of different views of the process and instrumentation diagram. So I think we had about 9 drawings in all, not intending you to actually look at the details of them, but just to show that there's an additional level of detail showing you all the instrumentation and controls associated with the various bits. So this would be going from Plant Ratcliffe to our metering stations. And so you can see that orifice metering station is actually a series of 2 that are used in parallel. This is the pig launcher, and there's an analogous one for our receiver. Our gathering and distribution hub, and then here's showing a metering station at the wellhead. And our project team met as a group with PCS and with what's called a HAZOP facilitator to do a hazard and operability analysis so that we walked through the operations and the controls associated with each part of the pipeline to identify hazards and to make recommendations for how to mitigate those hazards. And so, one of the findings of this are just changes to control logic or maybe small changes to controls itself or equipment in order to minimize the risk to the environment, to humans, and so forth. All right, so let's talk a little bit about routing of that pipeline. So I think you saw in George's slide, there was, maybe he showed a route and it's very straight lines, and that's just a way to just show it at the early stage of the project. We actually dug into specifically what was on the ground and how to route that, considering the owners of the land, the roads, the environmental conditions, like what wetlands are present. So all of that was considered. We put 100-foot buffers away from cultural and archaeological resources, and then considered advanced construction methods to get ourselves through wetlands, or when we had to go through them, but also trying to avoid wetlands when we could. So this is what the route looks like as drawn. So we're actually taking the CO2 off the top of Plant Ratcliffe here and coming around, and this is the pipeline coming here. This is a little junction where we're going off to one of the wells. And this is also where our gathering and distribution hub is, and then that CO2 is returned and comes along here and goes to the other well pad. And you'll see in the next few slides, or the next slide I'll show you, I'll zoom into this little square here, which is called sheet 7, to show you some of the detail associated with that routing. There's a permanent easement that'll be shown, and it's about 50 feet wide. We showed the temporary workspaces required during construction. And so we move on to this slide. So this is an example of just that one sheet along the route. So you can see here's our pipeline coming in. There's different shadings that explain the types of installation that's going to be required. So anything that's in yellow here in the center is our open cut kind of. And then you can see where we're crossing roads here. We've got these blue sections where we're boring. And then we're going through here, which is a wetland section. So these red sections here are showing that we're using HDD, and then we've got these purple segments that show us the permanent easement, and these are the workspaces and so forth. So it's a very detailed analysis looking at what land gets used in a temporary basis and on a permanent basis associated with this pipeline. So a route corridor summary, our total length of pipeline is 43,000 linear feet, which I think is about 13 kilometers. Horizontal directional drilling, or HDDs, we have 3 of them for just about a mile or 1.6 kilometers, 16 bores, 4 road crossings, no pipeline crossings were part of this. Also, as part of the FEED study, we have some layouts for the equipment that would be located at Plant Ratcliffe and at the the wellheads, the injection wells themselves. So this is just showing the CO2 coming in through the orifice, space allocated, this is very rough for the orifice meter, and leaving the Plant Ratcliffe station and the space allocated for that pig launcher. And then likewise, this is the gathering and distribution hub. So here we're coming at the CO2. Here's the space allocated for all the CO2 coming from Ratcliffe and our future tie-ins, and then going off to one of the wells and off to maybe some future wells. And then the orifice meter and coming into the well pad that's located really close on site here. So we have just one disturbance for both the hub and the well pad. That will go to the project schedule. We have a 96-week project schedule. So we're going on just about 2 years. So you can see the engineering phase of it is the first half of that schedule. And then the permitting process extends a little bit farther beyond that, so just over a year into the project. Rights of way acquirement is also about the same period of time. We have an ongoing survey task because we'll be doing that throughout the project, including through and the end of construction. So that's shown as a long piece, but it's not necessarily continuous throughout. A period of time about halfway through the project where the construction RFP or request for proposals, and then we have our construction happening towards the end of that project. So some risk and information gaps that were identified by PCS as part of the speed study is that costs are a big component. We all know, we've heard about, we've got supply chain issues. There's been a lot of escalation of costs. So procuring that pipe as quickly as possible when this project gets executed would be needed to guard against those increases. PCS has also seen a lot of trouble with market availability of valves, and so that's considered a risk that would need to be mitigated. Of course, getting the approval from the landowners and the access to it is going to be a big one, and the permitting associated with that. And then construction mats. There's like 4,000, I think, construction mats associated with this project, and they consider that a large and considerable cost, and that there's actually different qualities that different contractors require, and so that's also an uncertainty to take into account. So these are just a few of the ones that I thought I'd call out. And that brings me to the end of the slides that I have. So here's our contact information. My email address is here, as well as the one for project consulting services if you wanted to get in touch with them.